How are we doing? Did you check your line path? That information popped out this morning. Okay, so it's good it's popped out, and there's some complication as well. I will tell you. So for this class, 484, there are 4 sections taught by 3 different professors. All 4 sections are scheduled in the same room. Are we okay with that? I have to talk to the other 2 professors, what they think. If we agree upon cut the room somehow into 4 cubicles, each section goes in. Otherwise, you don't want to take the test of the other professor's problem, right? I'm sure you want my problems, right? Okay, so stay tuned. I have to talk to the other 2 professors. We'll figure it out, some agreement, or another option is go to the secretary and complain. That means going through a chain of secretaries. And I don't know if it can be solved or not. All right, so I'll let you know. Okay. So we continue our study on the duality. I would pick up what we left last time. And I would like to fuss over that example a little bit more before we let it go. So what I will do, I put up those 2 problems without the related word problems. Okay, so we had a minimization problem, the original problem. It's not the best location. I would like the problem to be on the board. And then this will be down. May I start over here? It will be better, and then we'll erase it. Okay, let me start from here. So I'll just put up that problem again. Minimize. Subject to. You have this on your note, so you don't have to copy. Bigger than 60. Okay, so that was the farmer's problem, and the solution is obtained. So the mean value is 144, obtained at x1. 6 is x1, 21 is the value of x2. Okay, so you know the meaning. He need to buy 6 units of feed 1 and 21 units of feed 2. That is to minimize his cost. That's the best choice, right? Okay. And then the other problem closely associated to this from the competitor, we call this a dual. We'll properly define it. Maximize. Now I have the following. We derived it last time. 60y1 plus 84 y2 plus 72 y3 subject to. Here I have 2 constraints, 3y1, 7y2, 3y3 less than 10, 2y1, 2y2, 6y3 less than 4. Okay, so that is viewed from the perspective of the competing salesperson try to grab more business, right? These Y1, Y2, Y3 will be the price of each tablet contains 1 unit of nutrients, nutrition value A, B, and C, okay, element. Okay, so we asked the question last time, can they strike a deal? Under what condition would they strike a deal? So the salesperson will go about and trying to solve his maximization problem. I don't know, maybe he has Excel, or he can use LP Assistant, or he knows linear programming. He solves it, and he would find some prices he could offer for each pill so that he can maximize his profit, right? And he would like to have that, okay? So is it fair to say that if the maximum he shall find here would match the min the farmer finds there, then they can agree upon that point. Then there will be a deal. Agree? Do you think that will be the case? We know how to solve this problem, right? Shall we go to LP Assistance? That's what I plan to do. Now, what's happening? Select a source. I am logged in. Okay, so let's see. Make screen. With LP Assistant, this should not take long time to solve. So I open that and let's punch in the problem. So we have 3 variables, and then we have inequalities. So you can add 2 slack variables. Let's do it mental. You add y4, you add y5, and it's in canonical form, right? You can punch those numbers in right away, and let's do this. So I need to add 1 regular variable and add another regular variable, and let's put in the numbers. So what do I have? 3, 7, 3, 1, 0, and the right-hand side is 10. And the second will be 2, 2, 6, 0, 1, and that will be 4. And x4 is the basic variable. The slack variables are basic. And the objective function, now this is a maximizing problem. Our LP Assistant deals with minimizing. So I need to make all the coefficients opposite sign. Is that clear? So negative 60, and the next will be negative 84, and the next will be negative 72. And that's all. Is that right? So let's go to solve it. Pivot. Okay. Following our procedure, let me make the window slightly longer. I need to do a couple of pivot steps to get to the answer. So I see this is the biggest negative number. I will choose this column, and let's check the ratio. That's 2, and that's less than 2. So I shall click on the 7. We agree? Let's do that. All right, and then I see I have 2 negative coefficients. This is more negative. Let's check this column. That's 0.22 and 33, so that's smaller. I'm going to click on that. Now I have 1 negative. Let's check the ratio. 1, 4, so I need to click on this. Can we all do that quickly? This problem can be solved in 2 minutes if you launch it and punch in the number, right? Not more than 2 minutes. Okay, now they're all positive. So the problem is solved. So what do we have? We solved. What will be the max value? Well, we solved the minimization problem. The minimum value will be negative 144, so the max value will be 144. Is that right? I did get that by doing negative twice. It's not just that number. So max is 144 cents obtained at what? So x1 is 1, x2 is 1, and x3 is 0. Is that right? Okay, so this only take x as variable. For our problem, we have y. So let's write it out for y. So y1 is 1, y2 is 1, and y3 is 0. So can you explain this answer in English for this salesperson? He did this calculation without letting the farmer know, and he found out that if he charges 1 cent for pill A and 1 cent for pill B and give pill C out for free, he maximizes his profit and will make the deal attractive to the farmer. Is that right? And for his own profit is 144. Is exactly the solution to the problem that the farmer solved, that he tried to minimize his cost. So I think they can have an agreement, isn't it? At least the salesperson can say now, okay, limited time, I give you this offer, only 1 cent for tablet A and 1 cent for tablet B, but I'm in such a good mood, I'm going to give the tablet C for free, just for today. Tomorrow I'll change my price, so take the offer or not, right? You can do that. So, okay, so we see that they could reach an agreement in this problem. So before we move on, let's make some observation. So we claim that this is the dual of that. Okay, we still have to properly define. But then let's observe the relation between these two problems. How is this one related to the original one? So let's say the original problem is a linear problem, L, and this is we call it dual, but we'll define it, okay? How do we start from L and get the D, and what are the relations between these two models? So let's first observe that. First we see that the objective is different. This problem is minimizing, and now he's changed into maximizing. Is that right? So min changed into max. So from L to D. Okay? That's the change I make. Okay, and the second observation, I see that for the original problem, I have all bigger than equal sign as my constraint, and here they're all changed into less than equal. So the inequality sign is flipped, isn't it? So here in this particular example, bigger than equal is changed into less than equal. Is that right? That's another obvious observation. What else do we observe? 3. So for the original problem, we have 2 unknowns, 2 variables, and 3 equations. And then here I have 3 variables and 2 equations. So the number of equation and variable are switched. Do we see that? So number of variable and number of constraints, to go from L to D, we switch it. Okay, anything else? Let's look at the central part of the constraint, this block here. And let's look at this block, the left-hand side of the constraint. In particular, the coefficients. So, say, where do I get these numbers 3, 7, 3? It's not random, right? Doesn't it come from there? It's the 3, 7, 3. Is that right? And then here I have 2, 2, 6 and I see 2, 2, 6. So if you shall form a matrix with these coefficients, then this matrix is exactly the transpose of that one. We see that? We'll get into that. Okay, so coefficient matrix, okay, we will work on that, and we see that I need to transpose it. It's transposed to get to the other one. All right, that's that. And let's look at the objective function. So for this objective function, in particular the coefficients, I have 10 and 14. Where do they end up in the other problem? The constant vector, right-hand side. Is that right? And the objective function here, these coefficients, 60, 84, 72, where do they come from in the original problem? The right-hand side. So the coefficients for the objective function and the vector in the constant column, they are again switched. Is that right? Okay, so they're so tightly knitted together. So let's see, coefficient of objective function and the constant column in the constraint. Again, these are switched. All right. Anything else we observe? Well, one observation we clearly made was that the solution for this problem, the max value here equals the mean value, right? So, okay, so the mean value in the end exactly matches the max value of the so-called dual problem we're claiming. Is that right? Okay, so these are observations by how we set up the other problem. This will be actually like property of the solutions. Okay? Anything else we observe? We see that the mean is obtained at the solution 621. x1 is 6, x2 is 21. Do you think these two numbers somehow pops up again in the other problem, or in the way we solve it, or in the solution, or anywhere? Do we see? Do we see a 621? I see it, 621. So what are they? They are coefficients in the objective function, the coefficients in front of the two slack variables, right? It's not coincident, okay? This is something that has to happen. So let's put it again. So that is the basic solution, right? So the optimal basic solution, so where you have the best choice, occurs as coefficients of slack variables when this max is reached in the dual problem. Okay, so that is later on another theorem, the slack variable theorem. Okay, so now you see these two problems are so tightly connected. Okay, just by observation, by taking this first example, then we of course we will do a lot more. Okay, so is it clear, this example? Now we go into something more really, how do you say, more rigorous, more structural. Now we will properly define the dual. Okay, so chapter 4.2. Oh, this takes a lot of writing. Okay, definition of a dual. the dual problem. Okay. Right, so now, again, we know that for linear programming problem, it can take so many forms. The constraint can be bigger than, equal to, less than, equal to. You can minimize, you can maximize. We need some starting point, a standard point that we can start talking about. So we will look at problems in a particular form. So this is a definition, number 1, a definition for a problem that's in a so-called max form. Okay, so we have a linear programming. We will call that it's in max form if I can write it as follows. Okay, so I'm going to write it. So this is a max form problem, so I will be doing maximize z equals c1 x1 plus cn xn. That's my objective. Subject 2. Okay, then I have to do this a11 x1 all the way to a1n xn less equal b1. So the max form is maximizing something, and the constraint is less than equal. Okay, that's this form. So all of it shall be, so I can have all these constraints. I write it down. am less than equal bn. Okay, x1 all the way to xn bigger than 0. So this is called a max form. Okay, and we also call it this is a max problem. Okay, just call the max problem. So is it clear what is a max problem? It's something you can write like that. Okay? And then I will define something totally symmetric. I will do a mean form. That's my second definition. Definition 2. I would define a mean form. A problem is in the mean form, or I can say this is a mean problem if I can write it as follows. Okay? So I will be minimize z c1 x1. So minimize some problem, or some objective function, and I have constraint, and now the constraint will have bigger than equal sign. So I basically will copy this down and I'll write bigger than equal. So let me do it. That's the first one. A m1 x1 a m n xn bigger than bn. And of course, I always have that. Okay. So you are minimizing something, and your constraint is bigger than equal to something. Is that clear? These two definitions? It's just for the convenience of the discussion that we'll have. We need some starting point. Okay. All right. Okay, so now we will define what we mean by a dual. We will take the max form as the starting point. So you have a problem that's given initially. It's in a max form, and you can write out the dual. All right? So we'll call the following definition number 3. Okay? This is just defined. We just call it. There's not derivation or anything. So the dual of the max problem is. So taking the max problem, I'm going to form a dual problem. So let's see. I will have the following problem. Minimize. Now, keep in your mind the observation we had of that example. Okay, so I will be minimizing. Now I call my unknowns y. So I will have b1, y1 plus b2, y2 plus all the way to bm, yn. So now I have m variables. Okay, so the number of variables equals the number of equations, constraints here. Okay, subject to. Okay, I'm going to transpose that A matrix. I will write it A1, 1, Y1 plus. I'll take the first column. It will become the first row. So I have A M1, Y M. And I will change the inequality sign bigger than equal. And I take the coefficient here, C1. That's what I do. That's for the first constraint, and you can do it for all of it. A 1n, y1 plus all the way to a m n y m. Okay, and bigger than c n. And all the y's are bigger than 0. Is it clear how a dual is formed once you have a max form? So let's see what we do. The center part of the constraint is by transposing this matrix and then change all the x into y, right? And the inequality less than equal are all changed into bigger than equal. And the right-hand side, the constant vector now appears as coefficients in front of the y's in the objective function. And the coefficients in the old objective function now appears as the constant on the right-hand side. Is that clear? You just do that and you form a new problem. This is what we define to be the dual of the max problem. Is okay? Okay, take a look at this dual of the max problem. Do you realize that, isn't this in that form? In the mean form? It's minimizing something, and all the constraints are bigger than equal to? Isn't that a mean problem? So make that observation. So I'll make this. Okay, so this dual is a mean problem. Okay. Let's take an example, just practice in concrete numbers of how to form the dual if you are given a max problem. Okay, might be a bit redundant, but will be useful to see. Example. Okay, let's say write out the dual problem of the following. So I have a following max problem, maximize, let's say x1 plus 3, x2 plus 5, x3, just numbers, subject to, let's see, let's put two constraints. So I have x1 plus 2, x2 plus 3, x3 less than 10. It's just number 4x1 plus 5x2 plus x3 less than 15, x1, x2, x3 bigger than 0. So how would you write out the dual? So you see that's a max problem. They're maximizing something and the constraints are less than equal to, right? Okay, so all you need to do is just strictly follow the definition and write it out. So how many variables will I have for the dual problem? We'll have 2. The number of variables in the dual will equal to the number of constraints that you have in the original, right? 1 for each. So this will associated with a y1, and this will associated with a y2. Those are the 2 variables. Okay, so I will be having a mean problem, right? Minimize the following. What will be my objective function? How do I form my objective function? The objective function, you take the right-hand side and multiply it onto y. Is that right? So I will have 10 y1 plus 15 y2. Is that clear where I get those numbers from? Mm-hmm. All right, subject to. Okay, so before I write out the constraint, how many will I have? Just have some expectation. The number of constraints will equal to the number of variables in the original problem. Is that right? So I have 3. Okay, keep that in mind. Okay, so let me form my first one. So you know, you can either visually transpose this, or you can, instead of going horizontal, you can go vertical. Is that right? So these coefficients will be multiplied, all these coefficients will be multiplied by y1, these will be multiplied by y2, and you add them vertically, and they shall be less than the coefficient in the objective function. Okay, so let's do the first one. So I have 1 times y1 plus 4 times y2, and that shall be bigger than equal to the coefficient in the objective function, that x1 position. Is that clear? All right, let's do the following. It's a bit faster. 2, 5, and that shall be bigger than 3. And the last one, 3. That shall be bigger than the coefficient 5. Right, and then y1, y2 bigger than 0. Yeah. Is that okay? Okay? It's not bad, right? You're just strictly following it. Now, the annoying thing of doing it like this, if I want to explain anything, theoretical, whatever, I'll have to write out a general expression for n equations. That's so heavy, this notation. It's a bit irritating, don't you agree? We have taken 220, haven't we? There's a much shorter, more compact way by using matrix and vector, right? Let's get into that. I know you can't wait. You've been waiting a whole semester to get into that. Let's do that. I will use matrix and vector notation. Okay? I will collect the coefficients there in a matrix, and then I will call it A. Let's say A will be just all the coefficients in the max problem. So A11 all the way to A1n and AM1 AMN. So this is a matrix of n column and m rows. It's not a square matrix, right? It's a rectangular shape. Is that clear? All right. And I will define a vector B to be the right-hand side. So B1 all the way to Bn. That's the B. And then I'll define the C. That's the coefficient in front of the objective function. So C1 all the way to Cn. So all the vectors are column vector, okay, by my definition. If you want a row one, you have to transpose it, okay. And then my vector of unknown is my x, x1 all the way to xn. And the unknown for the dual, I call it y, form the vector y1 to ym. Okay. And these vectors are of different lengths. Okay. So c and x, they have the same length. The length is n. And b and y, they have the same length, which is m, but they are different from the length of these two. Okay. All right, I am sure you know what is a transpose of a matrix. If I write A with a T on the top, then I transpose the matrix. You can think you have this A matrix, and then I just flip it and rotate 90 degrees. So the first column here will be the first row. It will be just switched, right? Are we all familiar with that? All right? Okay, so I will have A11 to AN1, and going down A1N, AMN. Okay, so this matrix will have N rows and M columns. It will be slightly, it's just transposed. And now we need to properly express the objective function by those two vectors. We have a vector c, we have a vector x, and the objective function is computed by multiplying them element-wise and sum it up. Isn't that familiar to us? What do we call that if you have two vectors and you do that operation to those two vectors? Is some kind of a product? Which one? Cross product? Dot product? Are we familiar with that? Dot product, we have heard? Let's introduce that. So, dot product. It just makes everything so compact, and I can write it. Okay, so take the example of x and c. If I say x is a vector, dot product, the c vector. Okay, c dot x, what does it mean? It means c1, x1 plus all the way to cn, xn. So if you take a dot product of two vectors, those two vectors must have the same length, otherwise you can't do it. Okay? And then you know this can be expressed as a product of if I transpose the c into a row vector and multiply it onto a column vector, then I get a number. That's exactly what that is, right? And then I see if I transpose the other way, x transpose times the c vector, so that's a row, that's a column, it gives me the same number. Okay? So this means this is exactly x dot c. Okay? So the dot product is a symmetric operator. Okay? You can switch the order. Right. So, okay, so with this bunch of notation in our hand, we can write the max problem, our problem, in a very compact form, in one line. How would I write max problem? So, maximize. What would I maximize? Well, it's a dot product, right? Z equals C dot X, subject 2, what are my constraints? Oh, the left-hand side, I see that is a matrix and vector multiplication. That will give me a vector of those values, a column vector, and that shall be less than the right-hand side, which is now in a B vector. Is that clear? All right? And x is bigger than 0. Now, x is a vector. If I write x bigger than 0, that means every element in x is bigger than equal 0. Okay? That's what this means. You can think this is a 0 vector of the same length as x. Okay. So that's the max problem, and I can write its dual, which I know is actually a min problem. Okay, so minimize, let's call it V equals, now I will dot B with Y, subject to, what I have now is A. Now the coefficient matrix, you see it's transposed. So it's A transpose multiplied by the vector Y. Then I get a column vector of length n. And that shall be, okay, the opposite sign, bigger than C. And the Y is non-negative. Yeah. Isn't that so compact? Do we like it? Okay, so I will pour this out and use it whenever it's suitable. For examples, we'll go to the detailed form, and to prove stuff, we need this compact form, okay? Otherwise, it takes so much writing. All right. Okay, so let's that be there, and then I will make an observation first. Okay, so we define the dual right now on top of the problem in a max form. What if I have a problem that is not in a max form? What do? Can I define a dual for it? In another way, you can ask the question, if I have a different problem not in a max form, can I put it in a max form? Always, right? And if I can, then I can write out its dual by definition. So this observation is the following, and I say it's quite obvious. Let's just say it's observation, not even claim. We don't need to prove. So any LP problem can be put in max form. Okay, how? Well, just by these tricks. I'll just explain these tricks, and then it shall be obvious that you can do it. Okay. So how can your problem be different from the max problem? So first, you might have a minimization problem, not a maximizing problem. What can you do? How do you change it into a maximizing problem if initially it says minimize something? Have we done that somewhere when we put it in the standard form? We multiply the objective function by a negative one, right? And then you can do the, you can change minimizing into maximizing. So one can change minimizing problem into maximizing problem by multiply a negative one on the objective function. So, okay, so that's solved. Then all the problem can be a maximization. Okay, second, now what if in my original problem the constraints have the wrong inequality sign? What if I don't have less than equal? I have bigger than equal. What can I do? I want to change it into less than equal. Some constraints. Well, it's that same magic trick. Throw at it that's -1. It has to change the way, right? Okay? So, and inequality of, okay, bigger than equal can be changed to less than equal, again, this same silly trick, by multiplying -1 on it. Okay, the third situation is a bit more interesting. What if my constraint has an equal sign, right? Then it's not in the max form. Okay, then what do I do? And equal and equality constraint let's say I basically have capital A equals B, generically speaking. How can I express it into using inequality? Any suggestions? I want to write inequality because I know I can handle an inequality already, right? So what should I require? So in the end, I will have A equal B, but what I require is inequality. Suggestion? Anyone want to help me out? I want inequality. Can I throw an inequality here? Let's say A less than B. I throw in that, but then I see that's not the same, right? I want A equal B. What more can I require so that A will have to equal B? The other inequality, right? What if I require at the same time B less than A? Then A must equal B. Agree? So an equal condition now breaks up into two inequality with the correct inequality sign. Then I'm done. Is that okay? Any questions? Okay, we'll have examples on this. So by this observation, now we can conclude, okay, any linear programming can be put in the max form, can have a dual. Okay? So that's what I want to say. So any LP has a dual problem, associated dual with it. Okay, so how do you compute this dual? How do you find it? Well, you should take two steps, and broadly speaking. So the first step, you should put it in the max form. If it's not, by these tricks that we just talked about. And then once you are in the max form, well, you just form the dual by definition. And that's it. Is that clear? Okay, that's that. Okay, so we'll practice on that, but okay. Let's practice this on one specific question that is of interest to me. So I'm thinking of the following. So we started from the max problem, and we formed the dual, which is in definition 3 here, that's the dual of the max problem, which is a mean problem. Now, by my observation, any problem has a dual, so this mean has a dual as well. If I go through this procedure and find the dual of this mean, what do you think I will get? Will I get a new problem that I can further find another dual, and then I'll have a chain of dual problems of the previous one, or I get something else? Do you understand my question? What is the dual of the dual problem? Okay, so the question I want to ask, what is the dual of the dual problem? Okay, in definition 3. Okay, so a way to find this out will be going through this procedure and find its dual and see what we have. Is that right? Okay, I'll take 2 steps. Step 1, I'll try to change it into a max problem. put it in a max form, let's say. Put it in max form. I will use this compact notation with vectors. It's much faster to write it in that way. So, okay, I have the original max problem. Its dual is this one. Now I'm doing the dual of this problem. I want to see what I get. So first I observe that I have a minimization. So I need to change it into max, right? I want to put it in a max form. So I will change it into maximize by multiply a -1 on it. So maximize negative b dot y. Is that right? I'm messing up this problem here. Okay? Subject to. Okay, and let's look at the constraints. The constraint says A transpose Y bigger than equal to C. And it has the wrong sign. I want to have it less than equal to. So I'll multiply this by -1 again. Is it clear? So subject to, so I have negative A transpose Y. And then now I can flip the sign, negative C. Can I do it? Okay, so I'll bracket. Now this is the vector on the right-hand side, and Y is still bigger than 0. Now do we agree this is a max problem? It's maximizing, and it has less than equal sign, right? Now I can form the dual just by definition. So form the dual. Okay, so the dual will be, instead of maximizing, I will do minimize. What do I minimize? Well, if you have a maximizing problem, the minimizing will be take your constant vector here and dot product the variable. So now for the dual, I call my variable x because y is already used here. So I will take the constant on the right-hand side, which is negative c. I will dot with my variable, which is x. Okay? I'm just strictly following the definition. Subject to. Now how do I form my constraint? Okay, so the constraint is to take the A matrix and transpose it. So the A matrix here is this guy. So I have negative A transpose. That's my A matrix. I need to transpose this. Multiply by my vector, which is x, right? And now I have the dual will be bigger than equal. What does it equal to? The coefficient in the objective function, which is now negative b, right? Oops, sorry. Negative b and x bigger than 0. So is it clear how I form the dual? Just follow the definition. Strict. No mistake. All right. So, okay, I see so many negative signs and the transpose of a transpose. Let's see. What is this term? What do you think? If I transpose A and I transpose it again, what do I get? I get the A back, right? So what I would have here will be negative A x bigger than equal negative b. Is that right? And I have all these negative signs everywhere. Can I get rid of it? Get rid of negative signs. Okay, so if I multiply the objective function by a negative sign, I get rid of that negative, and then I will have a maximizing problem, right? I would maximize c dot x, okay? And, okay, subject to, and if I multiply -1 on this constraint, I have to flip the inequality. So I'll have a x less than b, right? X bigger than 0. So what did I get in the end? did I get a new problem? I get the original problem back. Is that right? So if you take the dual of the dual, you go back to the original problem. So let's put this down. That's kind of a general, right? We're not putting any specific number. It's a general property. So the dual of the dual is the original problem. Okay. It's a kind of a similar to the transpose operator. So if you are my dual, then I am your dual, right? And then you go back if you apply the operator twice. Okay? All right. Is that okay? All right, so we have that. Okay, so next, what I want to do is to practice on these tricks to get us very comfortable by rewriting a general problem into a max form. And in particular, we have not practiced on trick number 3, and that's the one we're going to practice on. Okay, so let me go to the left and let me start from here. Okay, so let's take, so this is an example taken from the book. It's just different numbers. So, okay, I want you to find the dual problem of the following. Let's write out. Maximize, just numbers. Subject to. Okay, that's a nice one. Just numbers. Okay, something new is here. So I have a linear programming problem, which is not in the max form, and I want you to find the dual of it, okay? Not only is it not in max form, it has a new feature that we haven't really talked about. It has an equal in the constraint, okay? So let me circle that later. And then we want to see how to handle it and what it brings in the end into some new feature coming into the problem. Okay, so answer. You know, we need to take 2 steps. First, we have to write it into a max problem, then we can form the dual, right? So let's do the first step. Put it in max form, because it's not in a max form. Okay, so this takes a lot of repetitive writing, so let's be patient. So maximize, that is not changed. I'll copy it down. Constraint. And the first one is okay, it's already less than, so I copy. Now the second one, it's equal, so I need to break it into 2 inequalities, right? So here says A equals B, so I need to write A less than B and B less than A, right? So A less than B, let's write that out. X1 minus 2, X2 plus 3, X3 less than 20. And for the other one, I can multiply a negative sign. I will have the following: negative X1 plus 2, X2 minus 3, X3 less than negative 20. Is that okay? So this is A less than B. If I wrote here A bigger than B, and then I have negative A less than negative B. All right? Is that okay? Just a silly trick. Okay, and I have X1, X2, X3 bigger than 0. Now it's in max form. Is that right? I can form the dual. Step 2, form the dual. Just follow the definition. So how many variables should I declare for the dual problem? That would equal the number of constraints, which is 3. Is that right? So for each constraint, I associate with one variable. So y1 and a y2 and a y3. So these are all bigger than 0, bigger than 0. I associate each with a variable. Okay? And I have an objective function. Now I will be minimizing. Okay, so the objective function is take the constant vector and dot product the y, right? So 15 y1, 20 y2, 20 y3. Okay? Subject to how many constraints will I have? Well, that will equal to the number of variables, 3, right? And I will add them vertically up. So I hope this step is obvious, okay? 3y1 plus y2 minus y3. You take those coefficients and multiply by the y's. And then I will have bigger than equal to the coefficient in front of x1 there, 6. Is okay? I'll write out the second one without much fuss. So 7 y1, 2 y2, 2 y3, bigger than 1. And the third one, y1, 3 y3, 3 y2, 3 y3, bigger than 4. Right now, I have y1, y2, y3 bigger than 0. That is just to form it strictly following the definition, not doing anything to it. Can we all do that step? Is that clear? Right. Now I'm seeing something a bit funny. I see that y1, y2 and y3, everywhere they occur, they always have the same coefficient in the front with opposite sign, meaning y2 minus y3 always appear together. Do we see that? So let's see. If I jump on that observation and I rewrite it, just some simple manipulation, I have the following. I take out 20, then I have y2 minus y3. Can I do that? Subject 2. I have 3y1. I see I have the same thing here. I get y2 minus y3. They always appear together in this way. 7y1 minus 2 y2 minus y3 bigger than 1, and y1 plus 3 y2 minus y3 bigger than 4, and I still have the positivity of all these three by the definition when I form the dual. Now I see y2 and y3, they only appear in this form, meaning what matters to this problem is the quantity y2 minus y3. Is that right? Not y2, y3 on its own. It's this quantity that matters. How about I call this a new variable? Will that be okay? Should I call this y4, which is simply y2 minus y3? Can I do that? Well, I can, right? I can call it by anything. Then I rewrite my problem. What do I have? I have minimizing 15y1 plus 20y4, subject to, I should actually go up. This is kind of important, but okay. 3y1 minus plus y4 bigger than 6, and 7y1 minus 2, y4 bigger than 1, y1 plus 3, y4. These are my constraints, right? By just rewriting this into y4, now my variables for this new problem, I have only two variables now, y1 and y4. And I need to declare their sign. What I know is y1 is still bigger than equal to 0. That hasn't changed. What about y4? What do you think happens to y4? How did I define y4? Is the difference between y2 and y3. Is that right? And I know y2 is positive, y3 is positive. But I don't know about y2 minus y3. We agree? It could be any number. So you cannot put here y4 is positive, isn't it? You can't conclude. So y4 is now unrestricted. That's a bit strange, huh? Let me block this. Catch attention. Wow, that's something new. Where does it come from? What's causing this? A variable that's unrestricted. Where do you think it came from? Because in a standard problem, if I have less than equal sign, I just get to the dual with all positive variables. Why now I have an unrestricted one? It's because I had an equal there. Is that right? That's the new feature. So you know that if you have less than equal sign, you assign three variables by the definition of the dual problem. They will all be positive, and you can form the dual. And by artificially breaking an equal restrict into two inequalities, these two new variables in the end can, like kind of a combined force, it has actually just one effect to the final problem, right? And actually these two, y2, y3, actually has only one effect. So you can think y4 comes from this constraint, and because you have equal sign, as a consequence, y4 is unrestricted. Is that clear? Is okay? Right. Okay. So next time we will summarize, and okay, I'll give a couple more problems. So maybe I will modify the homework because I didn't finish this chapter. Okay, I'll save these problems for the next homework. Okay, any question?
Yeah, the attendance sheet.
It's somewhere. Attendance sheet, who has it? It's in the back, yeah. So make sure you sign on it. All right, then have a nice weekend.